It is late, and you have arrived here. Whether your day was kind or difficult, this hour is yours to rest. Let the small worries that climb into the dark slip back beneath the surface. Tonight we will drift very slowly into the ancient volcanic landscapes of the world, where the slow, patient fires of the earth have been quietly working for billions of years. This is the Circadian Institute. We exist for the long nights, for the in-between hours when the body is ready to sleep, but the mind is still moving. Tonight, our subject is the volcanic story of our planet, a slow, patient world of glowing mantle, drifting continents, dormant cones at twilight, deep ocean ridges, and distant volcanic moons, all moving across geological time in their own quiet way. If this kind of slow journey suits you, subscribing keeps these nights arriving. Let your body settle. Feel the support beneath you. There is nothing you need to do tonight, nothing you need to remember. The earth itself is already turning without you, slowly, quietly, exactly as it should. Tonight we drift into the slow volcanic story of our planet, toward the glowing core, the drifting plates, the dormant cones at twilight, the deep ocean ridges, and the volcanic moons of distant worlds, toward a kind of patience measured in millions of years. The journey is slow on purpose. There is no part of this story that requires you to stay awake. If you fall asleep before we are finished, that is the right ending. Let the bed hold you, and let the patient volcanic story begin. To begin the story of volcanic Earth, we have to begin very deep, deeper than we can see, deeper than we can drill, deeper than any creature has ever been. We have to begin at the very center of our planet, in the slow glowing heart of the earth itself. The earth beneath our feet is not solid all the way through. It is in fact mostly molten in its deeper regions. Beneath the thin crust where we live, beneath the soil and the bedrock and the mountains and the ocean basins, lies a vast hidden world of slowly moving rock, glowing metal, and patient pressure that has been working quietly for over 4.5 billion years. Geologists divide the inside of the Earth into several layers, each one with its own character. From the surface inward there is the crust, the mantle, the outer core, and the inner core. Each layer is made of different materials, behaves in different ways, and plays a different role in the slow story of our planet. The crust is the layer we know best, because it is the layer we live on. It is also by far the thinnest. Beneath the continents, the crust averages about 30 kilometers in depth. Beneath the oceans, it is even thinner, only about 7 kilometers thick. Compared to the size of the whole Earth, the crust is almost like the skin of an apple, a thin protective covering over a much larger interior. Beneath the crust lies the mantle, which is by far the largest layer of the Earth. The mantle extends from the bottom of the crust all the way down to about 2,900 kilometers below the surface. It makes up roughly 84% of the Earth's total volume. Almost everything beneath your feet in terms of sheer mass is mantle. The mantle is mostly solid rock, but it is rock under such enormous pressure and at such high temperatures that it can flow very slowly like an extremely thick syrup. Over millions of years, the mantle moves in great slow circulating currents, carrying heat from the deep interior up toward the surface and then sinking back down again. This circulation is called mantle convection. Mantle convection is one of the most important processes on our planet. It is what drives the slow drift of continents. It is what feeds the world's volcanoes. It is what keeps the surface of the Earth alive and changing, even on a time scale measured in millions of years. The mantle is, in some sense, the slow, patient engine of the entire planet. Beneath the mantle lies the outer core. The outer core is the only layer of the Earth that is entirely liquid. It is made mostly of molten iron and nickel, swirling slowly at temperatures that approach 4,000 degrees Celsius. The currents in the outer core, like the currents in the mantle, move on scales of geological time, slow, vast, and constant. The slow swirl of liquid iron in the outer core is what generates the Earth's magnetic field. The motion of all that conducting metal creates electrical currents, and those currents in turn create the magnetic field that surrounds our planet. This is the field that protects life from the harsh radiation of the sun. The deep core, in some sense, is the source of the invisible shield that wraps the entire Earth. At the very center of the Earth lies the inner core. The inner core is solid, a sphere of nearly pure iron and nickel, about 1,200 kilometers in radius, roughly the size of the Moon. It is solid not because it is cool, but because the pressure at the center of the Earth is so enormous that even at temperatures of over 5,000 degrees Celsius, the metal cannot melt. The temperature at the inner core is in fact hotter than the surface of the sun, and yet because it is held under such immense pressure, the iron there forms an enormous crystal lattice, a single solid sphere, slowly growing larger as the Earth gradually loses heat over billions of years. The inner core, deep and hidden, is a slowly crystallizing world all its own. All of this hidden architecture, crust, mantle, outer core, inner core, sits beneath every step you take on the surface. Every place on Earth, no matter how stable it seems, rests on this slow churning interior. The deepest deserts, the highest mountains, the busiest cities, the loneliest oceans, all of them are floating, in some sense, on the patient slow furnace of the planet. The heat that drives all of this comes from two main sources. The first is the leftover warmth from the formation of the Earth itself, 4.5 billion years ago, when countless smaller bodies collided to form the planet. The second is the slow, steady decay of radioactive elements deep within the mantle and the core. Together, these two sources keep the inner Earth warm enough to flow, even after billions of years. Some of this heat slowly works its way upward through the mantle toward the crust. When it reaches the underside of the crust, it can sometimes melt small pockets of rock into magma. The magma, being lighter than the surrounding solid rock, slowly rises through cracks and weak places, gathering in chambers beneath the surface, waiting patiently for the moment when it might emerge. This rising magma is the seed of every volcano on Earth. Whether the volcano is a tall, snowy stratocone in the Andes, a low, gentle shield in Hawaii, or a deep undersea ridge in the middle of the Atlantic, they all begin in the same way. They all begin as slow, patient heat, working its way upward from a planet whose deep interior has been quietly molten for billions of years. It is a strange thing to consider on a quiet night that beneath the calm bedroom of the world lies a vast, slow furnace, that the ground we trust to be solid is, on a longer time scale, fluid and moving, that the mountains around us are temporary expressions of forces we cannot see, that the entire surface of the earth is, in some sense, the visible skin of a much larger inner story. The slow inner earth does not know we exist. It does not know that there are creatures on its thin outer shell, watching the stars, building languages, falling asleep at night. It simply continues its slow, patient work, as it has for billions of years, indifferent to what happens on the surface, faithful only to the slow physics of heat and pressure and time. And yet, without that slow inner work, none of the surface story would be possible. The volcanoes would not exist, the mountains would not have risen, the continents would not have drifted, the atmosphere would not have been replenished by volcanic gases. Even life itself in its long history on Earth has depended on the slow, patient warmth of the inner planet. Tonight, while you rest, the inner Earth continues its slow circulation. The mantle is still convecting, the outer core is still swirling, the inner core is still slowly crystallizing. Magma chambers beneath the surface are still gathering, slowly, patiently, in places they have been gathering for thousands of years. There is something companionable in that slow inner activity. The way it has been going on long before any human civilization, the way it will continue long after, the way it does not require our attention or our understanding to keep working. The slow inner earth is steady company in its quiet, patient way. Let the thought of that slow inner warmth rest gently in your mind. There is no need to grasp it tightly. The earth has been holding itself together for 4.5 billion years without anyone supervising it. It will continue very patiently through the night and the morning and the years to come. And let us continue our slow journey very gently toward the next layer of the volcanic story. The crust of the earth, that thin outer shell where we live, is not a single solid skin. It is broken into a number of large pieces called tectonic plates. There are about a dozen major plates and many smaller ones, fitting together across the surface of the planet like the pieces of a slow shifting jigsaw puzzle. These plates are constantly moving. Not quickly, of course. The continents drift at roughly the speed at which our fingernails grow, about 2 to 5 centimeters per year. But over millions of years, that slow motion adds up. The continents we know today have been carried into their current positions by the patient drift of the plates beneath them. If you could watch the surface of the Earth at 1,000,000 times the normal speed, you would see the continents glide gently across the planet. You would see oceans open and close. You would see mountain ranges rise and fall. You would see entire seas appear where there had been dry land, and dry land emerge where there had been seas. The slow surface of the Earth is in fact a quiet, ongoing dance. The plates float on top of the upper mantle, the layer of slowly flowing rock just beneath the crust. As the mantle convects, very slowly the plates above are carried along with it. Where two plates pull apart, new crust forms. Where two plates push together, mountains rise or one plate dives beneath the other. Where two plates slide past each other, the ground occasionally shifts in long, quiet slips. 200 million years ago, all of the continents were joined together in a single enormous land mass that geologists call Pangaea. From the air, if there had been any air to fly through, Pangaea would have looked like a vast horseshoe-shaped supercontinent surrounded by a single global ocean. There were no Atlantic, there were no Pacific. There was simply land on one side and water on the other. Slowly, beginning around 200 million years ago, Pangaea began to break apart. The first cracks opened in what is now the central Atlantic. Over many millions of years, the cracks widened, and a new ocean basin began to form between the pieces of the slowly separating continent. North America and Africa drifted apart. South America and Africa drifted apart. The Atlantic Ocean was slowly born. Even today, the Atlantic is still widening. The Mid-Atlantic Ridge, a long underwater volcanic chain that runs down the middle of the ocean, is slowly producing new crust along its length. North America and Europe, on opposite sides of the Atlantic, are drifting apart at a rate of about 2.5 centimeters per year. Iceland, which sits directly on the ridge, is being slowly torn in half. On the other side of the world, the Pacific Ocean is slowly closing. Its plates are sliding beneath the surrounding continents in long, slow subduction zones. The Pacific is, in some sense, the older ocean, a remnant of the great single sea that once surrounded Pangaea, now slowly being consumed back into the mantle beneath the edges of Asia and the Americas. Where one plate slides beneath another in a process called subduction, the descending plate carries water and minerals down into the mantle. As it sinks deeper, the heat and pressure begin to drive water and gases out of the rock. Those gases, in turn, lower the melting point of the surrounding mantle rock, producing pockets of magma that slowly rise toward the surface above. This is the process that builds the long volcanic chains around the edges of the Pacific. Where two continental plates collide, no subduction occurs. Instead, the crust crumples and folds upward, building enormous mountain ranges. The Himalayas were built this way when the Indian plate, drifting slowly northward, collided with the Eurasian plate around 50 million years ago. The collision is still going on. Mount Everest is still rising, very slowly, by a few millimeters every year. Where two plates pull apart on land instead of underwater, a long valley called a rift forms between them. The East African Rift Valley is one of these features. Over many millions of years, it will slowly widen, and the eastern edge of Africa will eventually break away to become a separate small continent, drifting slowly out into a new ocean basin that does not yet exist. Volcanoes appear most commonly along these slow boundaries between plates. The places where plates pull apart, where plates push together, where plates dive beneath one another, these are the places where the deep heat of the mantle finds its way most easily to the surface. The map of the world's volcanoes is in many ways a map of the world's plate boundaries. There is one important exception to this rule. A few volcanoes form not at plate boundaries, but in the middle of plates, above what geologists call hotspots. Hotspots are stationary plumes of unusually hot mantle that rise up from much deeper within the Earth, sometimes from near the boundary between the mantle and the outer core. We will return to these in their own chapter. The slow drift of continents is not a recent discovery. It was first proposed in the early 20th century by a German meteorologist named Alfred Wegener, who noticed that the coastlines of Africa and South America fit together remarkably well, like the pieces of a puzzle. He suggested that the continents had once been joined and had drifted apart since. For decades, his idea was dismissed as fanciful. It was not until the 1960s, with the discovery of seafloor spreading and the underwater ridges, that Wegener's idea was finally vindicated. The new understanding of plate tectonics, as it came to be called, transformed geology in a single generation. Suddenly, almost everything about the surface of the Earth made new sense. The volcanoes, the earthquakes, the mountains, the deep ocean trenches, all of them fit into a single, elegant, slow story. Today, geologists can measure the slow motion of the plates with great precision, using satellites that track the positions of fixed points on each continent. The continents are still moving, exactly as predicted. The Atlantic is still widening, the Pacific is still narrowing, India is still pushing into Asia, Africa is still slowly cracking open along its eastern rift. In 100 million years, if these motions continue, the world map will look very different from the one we know. Africa will have collided fully with Europe, closing the Mediterranean and pushing up new mountains in its place. Australia will have continued north, perhaps fusing with parts of Asia. The Atlantic will have grown wider still, while the Pacific will have continued to shrink. The continents we know today are simply a snapshot of an ongoing, slow rearrangement. In 250 million years, some geologists predict that all of the continents may once again drift together into a new supercontinent, sometimes called Pangaea Ultima or Amasia. The cycle of supercontinents forming and breaking apart appears to repeat every few hundred million years. Pangaea was not the first. It will not be the last. This slow cycling of continents is sometimes called the Wilson cycle, after the geologist who first described it. It is one of the great patient rhythms of our planet. Over hundreds of millions of years, oceans open and close, continents gather and separate, mountains rise and erode away. Nothing on the surface is permanent. Everything is in slow, gentle motion all the time. Tonight, while you rest, the plates beneath your feet are still moving. The Atlantic is widening by a hair's breadth each night. The Pacific is narrowing by the same. India is still pushing into Asia. Iceland is still being slowly torn in half along the mid-Atlantic ridge. None of this is happening fast enough for you to feel. All of it is happening exactly as it has been for hundreds of millions of years. There is something steadying in that thought. The slow drift of the continents has been going on through every night of every life that has ever been lived on Earth. It will continue through every night to come. The world is patient. It does not need to be hurried. The slow rearrangement of the Earth is a quiet companion to all of our small lives. Let us drift very slowly toward the next chapter of this slow story. If you were to look at a map of the world's volcanoes from above, you would notice something striking. The volcanoes are not scattered evenly across the planet. They are arranged in long curving chains, mostly along the edges of the great oceans. And one of those chains is so vast and so complete that it forms an enormous loop around the entire Pacific Ocean. This loop has a name. It is called the Ring of Fire. The Ring of Fire is by far the most volcanically active region on Earth. It contains roughly 3/4 of all the active volcanoes on the planet. It also contains about 90% of the world's earthquakes. From New Zealand in the south, up through the islands of Indonesia and the Philippines, along the coasts of Japan and Russia, across the Aleutian Arc of Alaska, and down the western coasts of North and South America. It traces a vast horseshoe of patient geological activity. The reason for this concentration is plate tectonics. The Pacific Ocean basin is surrounded by a series of subduction zones where the oceanic plates beneath the Pacific are slowly sliding underneath the surrounding continental plates. As the descending plates carry water and minerals into the mantle below, they trigger the slow formation of magma, which rises to feed the long arcs of volcanoes above. Each region of the ring has its own character. The volcanoes of Japan are mostly tall, steep stratocones with classical conical shapes that rise above forested slopes. Mount Fuji, the most famous, is one of the most photographed mountains in the world. It has been dormant since the early 18th century, standing quietly above the surrounding plain, like a perfectly drawn shape against the sky. Indonesia is the most volcanically active country on Earth, with more than 100 active volcanoes spread across its many islands. The volcanoes of Java, Sumatra, and the Lesser Sunda chain stand among ancient rice terraces and thick tropical forests. The fertile volcanic soil makes Indonesia one of the richest agricultural regions in the world, supporting communities that have lived alongside the slow, patient mountains for many generations. The Philippines, just north of Indonesia, also sits along the ring. Mount Mayon on the island of Luzon is famous for having one of the most perfectly symmetrical volcanic cones in the world. Mount Pinatubo, also on Luzon, has a wide, quiet caldera lake at its summit, slowly filling with rainwater between its long stretches of dormancy. Further north, the Aleutian Arc of Alaska forms one of the most remote stretches of the ring. Long chains of volcanic islands curve out into the cold waters of the North Pacific, with names like Akutan, Cleveland, Bogoslav, and Pavlov. Many of these islands are uninhabited, their volcanic peaks rising in solitary patience from the sea, often wrapped in low cloud and mist. Down along the western coast of North America, the Cascade Range continues the ring. Mount Rainier, Mount Hood, Mount Shasta, Mount St. Helens. These tall, snowy stratocones stand above the green forests of the Pacific Northwest. From the air, they look like a series of giant sleeping figures, each one rising thousands of meters above the surrounding land, each one a slow expression of the deep subduction beneath. Further south, the volcanoes continue down through Mexico and Central America. Popocatépetl, the great smoking mountain just east of Mexico City, has been intermittently active for thousands of years. Its companion Iztaccíhuatl lies beside it, dormant and snow-covered. The two mountains together feature in ancient Aztec mythology, which tells of two lovers eternally side by side on the high plateau. The Andes Mountains of South America form one of the longest continuous volcanic chains in the world. From Colombia in the north, through Ecuador, Peru, Bolivia, Chile, and Argentina, the Andes stretch for more than 7,000 kilometers along the western edge of the continent. Hundreds of volcanoes rise along this chain, including some of the highest peaks on Earth outside of the Himalayas. Ojos del Salado, on the border between Argentina and Chile, is the highest active volcano in the world, reaching nearly 7,000 meters above sea level. Its summit lies above the level where most clouds form. From the top, on a clear day, The curve of the Earth itself can be seen along the distant horizon. The mountain rests under thin air and bright sun, dormant for many centuries at a time. Across the Pacific, on the far western side of the ring, the long chain continues through the Kamchatka Peninsula of eastern Russia. Kamchatka is one of the most volcanically dense regions on the planet, with more than 150 volcanoes packed into a relatively small area. Many are remote, surrounded by pristine wilderness, visited only by occasional researchers and small groups of travelers. Each volcano in the ring is a slightly different expression of the same deep process. Some are tall and steep, with thick magma that builds up into classical cones. Some are broader and gentler, with thinner magma that flows more easily down the slopes. Some have wide caldera lakes at their summits, formed in long-ago collapses. Some are perfectly intact. The slow geology has produced a remarkable variety of shapes, all from the same patient underlying source. The ring is also home to most of the world's deep-sea trenches, where the oceanic plates dive down into the mantle. They create long, narrow valleys at the seafloor, often more than 10 kilometers deep. The Mariana Trench, the deepest place in any ocean, lies along the ring just east of the Philippines. The slow descent of plates into the mantle creates both the trenches below and the volcanoes above. Communities have lived along the ring for thousands of years. Many of the world's oldest civilizations grew up near volcanoes. The fertile volcanic soil supports dense agriculture. The geothermal heat warms hot springs that have been used for bathing and cooking for many generations. The ancient mythologies of every culture in the ring tell stories of mountain spirits, fire gods, and slow, patient earth forces woven into the foundational narratives of those societies. Despite its activity, the Ring of Fire is, on most days, remarkably quiet. Most of the volcanoes along it are dormant most of the time. They simply stand patiently at twilight or dawn or in midday sun, looking very much like ordinary mountains. The slow underlying processes that built them continue at their patient geological pace, mostly out of sight. Geologists watch the ring carefully. With networks of seismic sensors, gas detectors, and satellite measurements, they listen for the small, slow signals that indicate magma is moving deep beneath a particular peak. Most of the time, the readings show nothing unusual. The ring goes on with its slow, patient work, and the watchers go on with their slow, patient observation. The Ring of Fire is, in some ways, the visible face of the deep interior of the Earth. It is the place where the slow inner heat of the planet most readily emerges into view. Every peak along the ring is connected, deep underground, to the great patient circulation of the mantle and the slow descent of oceanic plates into the deep below. Tonight, the ring continues. Snow is falling on the high cone of Mount Fuji, somewhere in Japan. Mist is wrapping the slopes of an unnamed Aleutian island, somewhere in the cold North Pacific. Stars are emerging above the high summit of Ojos del Salado in the Andes. A soft, warm wind is moving across the dark slopes of Mount Rainier in the Cascades. The ring is mostly silent, mostly dark, mostly at rest. And beneath each one of those quiet peaks, the slow magma is still working its way patiently upward, just as it has been for millions of years. There is no hurry. There is no urgency. The ring of fire is in no rush at all. Let the slow patience of the ring rest gently in your mind. The mountains of the Pacific Basin are continuing their slow work, exactly as they have for millions of years, exactly as they will for millions more. There is nothing you need to do about it. There is only the quiet knowledge that they are there working steadily through the night. Let us drift very gently toward the inner workings of a single volcano. To understand a volcano, it helps to imagine cutting one open, very gently, the way a geologist might draw a cross-section in an old textbook. From the outside, a volcano looks like a mountain. From the inside, it is something more complex, a vertical pipe-like structure that connects the deep interior of the earth to the open air above. At the base of every volcano, deep beneath the surface, lies a magma chamber. This is a large pocket of molten rock that has slowly accumulated over many years, sometimes many thousands of years, in a region of weak crust. Magma chambers vary enormously in size. Some are small, holding only a few cubic kilometers of melt. Some are vast, holding hundreds of cubic kilometers of slow, patient liquid rock. The magma in the chamber is not, in fact, fully liquid. It is more like a slow porridge, a mixture of melted rock, suspended crystals, and dissolved gases. Depending on the composition of the rock and the temperature, the magma may be quite fluid or thick and sticky. Different chemistries produce very different volcanoes with very different shapes and behavior. Above the magma chamber, a vertical column of weakened rock often runs upward toward the surface. This column is called the conduit. The conduit is the path that magma takes when it moves upward. It may be wide or narrow, straight or branching, depending on the geology of the particular volcano. Sometimes the conduit forms suddenly, when pressure from below cracks new fissures in the overlying rock. Sometimes it has been there for thousands of years, slowly used and reused. At the top of the conduit, where it reaches the surface, is the vent. The vent is the opening through which magma, or the gases above it, emerges into the open air. Vents can take many forms. Some are simple round openings, some are long fissures that stretch for kilometers across the landscape. Some are buried beneath glaciers or beneath the sea. Around the vent, over many thousands of years, the rock that emerges from below piles up to form the visible mountain we recognize as the volcano. The shape of this mountain depends on what kind of rock has come out of it. Thin, runny lava builds gentle, wide shields. Thick, sticky lava builds steeper cones. Ash and cinder build small, loose hills called cinder cones. Each shape tells a story about the chemistry of the magma below. At the very top of the volcano, where the vent opens, there is often a depression called the crater. A crater is the bowl-shaped opening at the summit, where the upper layers of rock have been blown away or have collapsed back into the conduit during past episodes. Some craters are small and deep, some are large and shallow. Some hold lakes of cool, clear water that have slowly accumulated over the centuries. In larger volcanoes, the crater may have collapsed at some point into a much wider depression called a caldera. A caldera forms when the magma chamber beneath a volcano slowly empties, leaving the overlying rock unsupported. The roof of the chamber then sinks inward, often producing a vast circular or oval depression that is much wider than the original crater. Calderas can be enormous. The Yellowstone caldera in the western United States is roughly 55 kilometers wide by 70 kilometers long. The caldera at Toba in Indonesia is even larger, measuring around 100 kilometers across. Calderas this size are sometimes called supercalderas, and the volcanoes that produce them are sometimes called supervolcanoes. We will return to those in a later chapter. Beneath the surface, around the edges of the magma chamber, the rock is gradually heated and altered. Hot fluids percolate through the cracks in the surrounding stone, slowly depositing minerals and creating veins of crystallized rock. Over thousands of years, these veins can grow rich in valuable minerals, including copper, gold, and silver. Many of the world's largest mineral deposits formed in this way, deep around ancient magma chambers. On the surface around the volcano, hot springs and geysers and fumarolas often form. These features mark places where heated water from below reaches the surface. The water is warmed by passing through rock that is itself heated by the magma chamber far below. A volcano, even when it is not erupting, often quietly maintains a small geothermal world around its base. The lava that emerges from a volcano is, by another name, simply magma that has reached the surface. The two words mean almost the same thing. The difference is whether the molten rock is still inside the earth, in which case it is magma, or has already come out, in which case it is lava. The transition happens at the moment the rock crosses the vent. Once on the surface, the lava begins to cool. The outside cools first, hardening into a dark crust. The inside remains hot for much longer, sometimes weeks or months. As the outer crust hardens and the inner liquid continues to flow, the lava can take on remarkable shapes: long, ropey folds, smooth, glassy surfaces, jagged, blocky textures. The form depends on the speed of cooling and the chemistry of the rock. Inside the conduit, the magma may also be doing other things. As it rises and the pressure decreases, the dissolved gases inside it may begin to come out of solution, forming bubbles. These bubbles can grow as the magma rises, expanding rapidly in the lower pressure near the surface. The behavior of these gases is one of the most important factors in how a particular volcano behaves. Some volcanoes have very runny magma with relatively few gases. In these volcanoes, the gases escape easily, and the magma flows out gently as lava. Hawaiian volcanoes are like this. Their flows can be observed at fairly close range, slowly spreading over the landscape, sometimes traveling for many kilometers before they cool and stop. Other volcanoes have very thick, sticky magma with high gas content. In these, the gases cannot escape easily, and the pressure builds up over time. When the pressure finally finds a way out, these volcanoes can release their energy more vigorously. The Cascade volcanoes, the Andean stratovolcanoes, and the volcanoes of Indonesia tend to be of this kind. Long, quiet periods between brief releases of energy. Around the world, the architecture of volcanoes is enormously varied. Some are isolated solitary peaks, some are clustered in groups, some are part of long chains, some are barely recognizable from the surface, just gentle rolling hills that hide vast caldera structures beneath. Some are ancient and deeply eroded, some are young and pristine, only a few thousand years old. Each volcano is, in its own way, a kind of slow architecture, a building constructed by the patient release of material from below over enormous spans of time. The building is constantly being modified by erosion above and by the slow flow of magma below. No volcano is ever quite finished. They are all works in slow geological progress. Tonight, all over the world, magma is sitting quietly in countless chambers beneath the surface. Conduits are connecting those chambers to vents above. Craters are holding their gentle lakes. Calderas are sleeping under their snow. Hot springs around the bases are steaming gently into the cool night air. The architecture of volcanism is at rest, exactly as it has been on most nights for millions of years. There is something steady in that thought. The slow building of the volcanoes continues beneath the surface on its own patient timeline. The architecture is being shaped very slowly, even as the world above sleeps. The deep work of the planet does not need our supervision. It has been going on for billions of years, and it will continue exactly as before through the long, quiet hours of the night. Let the slow, patient anatomy of these mountains rest gently in your mind. The chambers, the conduits, the vents, the craters, the calderas, each one is part of a vast, slow story that has been unfolding far longer than any human life. Tonight, that story continues exactly as it should. Let us continue our slow drift very gently toward the next chapter, the many shapes of volcanoes around the world. Volcanoes come in many shapes. From a distance, some look like classical pointed cones rising sharply against the sky. Some look like wide, gentle domes, barely distinguishable from rolling hills. Some look like irregular, jagged piles. Some are barely visible at all, hidden beneath the sea or beneath the ice. The variety of shapes reflects the variety of processes that built them over many thousands of years. Geologists generally divide volcanoes into a handful of main types based on their shape and the processes that built them. The four most commonly recognized are shield volcanoes, stratovolcanoes, cinder cones, and lava domes. There are other less common types as well: calderas, fissure systems, submarine seamounts, but these four cover most of the volcanoes we see on land. Shield volcanoes are the largest type by volume. They get their name because, when seen from a distance, they look like a warrior's shield laid flat on the ground, a wide, gently sloping mound that rises only a small angle above the surrounding plain. Despite their gentle profile, shield volcanoes can be enormous in size, sometimes the largest mountains on Earth by total mass. Mauna Loa, on the island of Hawaii, is the largest shield volcano on Earth. From its base on the deep seafloor to its summit above sea level, Mauna Loa rises more than 9,000 meters, taller in total than Mount Everest. It is also enormously broad, covering more than half of the island of Hawaii in a single gentle slope. From most angles, Mauna Loa does not look like a mountain at all. It looks like a vast, slow swelling of the land. Shield volcanoes are built up over thousands of years by long, thin flows of fluid lava. The lava that builds them is rich in iron and magnesium, which gives it a relatively low silica content and makes it flow easily. Each individual flow may travel many kilometers from the vent before it cools, spreading out into a broad, thin sheet. Layer upon layer, over time, These sheets accumulate into the gently sloping mound of the shield. Stratovolcanoes, sometimes called composite volcanoes, are the classical pointed cones that most people picture when they imagine a volcano. They rise at much steeper angles than shields, often reaching 20 or 30 degrees of slope. They are typically taller and narrower, with sharply defined summits. Mount Fuji, Mount Rainier, Mount Vesuvius, and Mount Kilimanjaro are all stratovolcanoes. Stratovolcanoes are built up by a mixture of thicker, stickier lava and ash. The lava that feeds them is richer in silica, which makes it flow less easily. Instead of spreading out in long, thin sheets, the lava piles up near the vent, building steeper slopes. Between the lava layers are layers of ash and other loose material that has been ejected at various times. The alternating layers give stratovolcanoes their other name, composite volcanoes. Stratovolcanoes are often the most photogenic mountains in their regions. Their classical conical shape, often capped with snow, makes them stand out clearly against the surrounding landscape. They appear in the art and mythology of countless cultures. Mount Fuji is sacred to many in Japan. Mount Kilimanjaro stands as a great solitary cone above the East African plain, the highest mountain on its continent. Cinder cones are the smallest of the main volcano types. They form in relatively short bursts of activity, often only a few months or years long, when fragments of cooling lava are thrown out of a single vent and pile up around it. The fragments, called cinders, scoria, or tephra, accumulate into a small steep cone, usually only a few hundred meters tall. Cinder cones often occur in clusters. A single magma source may feed dozens of small cones across a wide area, each one formed during a brief period of activity at a different vent. The Auvergne region of France, the Mexican volcanic belt, and parts of the western United States are dotted with such cinder cone fields, each cone a small monument to a brief eruption from long ago. Lava domes form when very thick, sticky lava is squeezed out of a vent without much explosive force. Instead of flowing away, the lava piles up around the vent in a dome-shaped structure that grows slowly outward as more material is added from below. Lava domes can be small, only a few meters tall, or quite large, several hundred meters across. The largest of all volcanic features are calderas, the wide depressions formed when a magma chamber empties and the overlying ground sinks inward. Some calderas are simple bowl-shaped depressions a few kilometers across. Others, like Yellowstone or Toba, are vast features many tens of kilometers wide. Calderas often hold lakes, fed by rainwater that slowly accumulates in the depression over time. Crater Lake in Oregon is one of the most beautiful caldera lakes in the world. It formed about 7,000 years ago when the volcano known to geologists as Mount Mazama collapsed inward, leaving a wide circular depression that gradually filled with rainwater. Today, the lake is more than 900 meters deep, one of the deepest in the world. Its surface a perfectly still mirror of the surrounding rim and the sky above. Beyond these main types, volcanoes can take other forms as well. Mars are shallow, circular craters formed by the rapid cooling of magma when it meets groundwater. Tuyas are flat-topped volcanoes that erupted under glaciers. Submarine volcanoes, known as seamounts when they do not break the surface, are the most numerous of all volcanoes, with thousands of them rising from the deep sea floor of every ocean. Each type forms in a specific way in response to the specific conditions of its setting. The shape of a volcano is, in some sense, its biography written in stone, a record of the chemistry of its magma, the depth of its chamber, the rate of its eruptions, and the length of its life. To look at a volcano carefully is to read a long, slow story written by the patient work of the earth. Some volcanoes are very old. The Hawaiian volcano of Kohala began forming about 1 million years ago and has been dormant for more than 60,000 years. Some volcanoes are very young. Paricutin in Mexico formed in the 1940s, growing from nothing to more than 400 meters tall in just 9 years before going quiet again. The lifespan of an individual volcano can vary enormously. After a volcano becomes extinct, it slowly erodes. Wind, rain, ice, and time wear down the slopes, smooth out the cone, and gradually carry the rock away. After many millions of years, an old volcano may be reduced to a low, gentle hill, almost unrecognizable as the towering peak it once was. Some of the gentlest hills in old continental interiors are, in fact, the deeply eroded roots of volcanoes that died long ago. This long process of building and erosion means that the surface of the Earth is, in many places, a kind of geological palimpsest. Beneath the present landscape lie the worn-down remains of countless older volcanoes, layer upon layer, each from a different ancient era. To walk across an old continent is, in some sense, to walk over the buried graves of 1,000 vanished mountains. Tonight, all of these forms of volcano are at rest, somewhere in the world. The vast shields of Hawaii are still standing patiently above the sea. The classical cones of Japan and the Cascades are still rising sharply against their skies. The small cinder cones of the Auvergne are still scattered across their quiet plain. The wide calderas of Yellowstone and Toba are still holding their slow lakes. The slow architecture of volcanism is widespread and varied and at peace. Each one is a different expression of the same underlying patient work of the earth. Each one is a different shape carved by the same slow forces. Each one is a quiet companion to the long human story of looking up at mountains and wondering how they came to be there. Let the variety of these slow, patient mountains rest gently in your mind. They have been with us for as long as there have been people to look at them. They will continue in their varied forms long after we are gone. Let us continue our slow drift very gently toward the slow flow of magma and lava itself. Magma is the molten rock that lives beneath the surface of the earth. Lava is the same molten rock once it has reached the open air. The two are made of the same material. The difference is only a matter of where they happen to be at any given moment. Magma below, lava above. The transition happens at the vent. The chemistry of magma varies considerably from place to place. Some magmas are rich in silica, the same mineral that makes up sand and quartz. These are called felsic magmas. Some are poor in silica and rich in iron and magnesium instead. These are called mafic magmas. Between them lie intermediate magmas of mixed composition. The chemistry shapes everything about how the magma behaves. Felsic magmas are thick and sticky. They flow slowly and tend to trap dissolved gases inside themselves. The volcanoes they build are usually steep and tall, with shorter, quieter periods of activity separated by long stretches of dormancy. The famous stratocones of Japan, the Cascades, and the Andes are mostly built from felsic and intermediate magmas. Mafic magmas are thin and runny. They flow easily and let their gases escape gently. The volcanoes they build are usually broad and gentle, with longer, quieter activity that produces flowing rivers of lava rather than steep piles. The shield volcanoes of Hawaii and Iceland are built from mafic magmas. So are most of the undersea volcanoes that line the mid-ocean ridges. The temperature of magma also varies. Felsic magmas are usually around 700 to 900 degrees Celsius. Mafic magmas are hotter, often 1100 to 1300 degrees Celsius. The hotter the magma, the more fluidly it flows. The cooler the magma, the more it tends to stick and pile up. Temperature and chemistry together determine the personality of every volcano. When magma reaches the surface and becomes lava, it begins to cool. The cooling happens fastest at the outer edges, where the lava is in contact with the air or the water. The interior cools much more slowly, sometimes remaining warm for weeks or months after the surface has hardened. This is why lava flows can crack open as they move, exposing brighter inner glow beneath a darker outer crust. Lava can take on remarkable shapes as it cools. Smooth, ropey folds called pahoehoe form when fluid lava develops a thin, elastic skin that wrinkles as the molten interior continues to flow beneath. Pahoehoe surfaces look like coiled rope, twisted dough, or the intricate folds of pulled taffy. The Hawaiian word pahoehoe captures this smooth, flowing quality. Other lava cools into rough, jagged blocks called AA. Another Hawaiian word, AA lava, forms when the surface of a flow becomes too rigid to flex with the moving interior, breaking into sharp angular fragments that pile up on top of the still flowing rock beneath. AA surfaces are spiky and difficult to walk across, with sharp edges and loose tumbled blocks. Lava that flows underwater takes on yet another form. As the molten rock meets the cold sea, the outer skin cools almost instantly, forming a soft, elastic bag. The lava continues to flow into the bag, swelling it like a balloon, until the bag detaches and another forms behind it. The result is a stack of rounded dark pillows called pillow lava that builds up the structure of every undersea volcano. As lava cools further, it may crystallize into a variety of rocks. The most common is basalt, a fine-grained dark rock made when mafic lava cools relatively quickly. Basalt covers most of the ocean floor of the world. It also makes up the bedrock of the Hawaiian Islands, the Great Basalt Plateaus of Iceland, and the Columbia River basalts of the western United States. When basaltic lava cools especially uniformly, it can develop hexagonal columnar joints, long six-sided pillars of rock that form perpendicular to the cooling surface. The Giant's Causeway in Northern Ireland, the Devil's Postpile in California, and the basalt columns of Iceland all show this pattern. The columns are nature's geometry, written in cooling stone. Felsic lava, when it cools, often forms different rocks. Rhyolite is the felsic equivalent of basalt, a fine-grained, light-colored rock that builds many of the steep volcanic mountains around the world. Pumice is a frothy, lightweight rock formed from gas-rich felsic lava that cooled with bubbles still trapped inside. Some pumice is so light that it can float on water, drifting across oceans for many years before slowly sinking. Obsidian is yet another product of cooling felsic lava. When the lava cools so quickly that it has no time to form crystals, it solidifies as a smooth, glassy black rock. Obsidian breaks into sharp, curved edges, sharper than the finest steel. For thousands of years, ancient communities around the world used obsidian to make tools, blades, and ceremonial objects. The volcanoes provided the raw material for some of the earliest sharp instruments in human history. As lava flows across the landscape, it may follow the existing terrain or carve new paths of its own. In long-lasting flows, lava sometimes forms tubes, natural tunnels in which the outer surface has hardened, while the molten interior continues to drain away beneath. After the eruption ends, these lava tubes can remain as long, winding caves, sometimes stretching for many kilometers underground. On the Big Island of Hawaii, the Kazumura Cave is one of the longest known lava tubes in the world, extending for more than 60 kilometers in a continuous winding passage beneath the slopes of the Kilauea volcano. The tube was formed long ago by patient ancient flows, slowly draining away beneath their cooled outer skins. Today the cave is dark and silent, a quiet relic of long-vanished lava. Lava can also affect water in interesting ways. When a lava flow enters the sea, the meeting produces clouds of steam that rise gently above the contact zone. The water near the lava is warmed for a long distance around the flow, sometimes creating temporary microenvironments where heat-loving organisms thrive briefly before the flow ends. When lava enters a glacier, it produces immense quantities of meltwater. The Eyjafjallajökull volcano of Iceland in 2010 produced one of these meetings when a lava flow beneath the surface ice melted enormous volumes of glacier into a slow flood that drained gently away across the surrounding plain. The interaction of fire and ice has shaped much of the Icelandic landscape over the centuries. Volcanic ash, another product of magma reaching the surface, is composed of tiny fragments of rapidly cooled lava, small jagged glass shards smaller than a grain of sand. Ash can travel enormous distances on high-altitude winds, sometimes circling the globe many times before slowly settling out of the atmosphere. Ash from a single ancient eruption can be found in deep-sea sediments halfway around the world. Over time, settled ash forms layers of soft gray rock called tuff. Tuff is found on every continent, in layers thousands of meters thick in some places. The pyramids of Cholula in Mexico are built on a base of ancient tuff. Many of the rock-cut churches of Cappadocia in Turkey were carved into thick layers of tuff laid down by long-vanished volcanoes. The slow material of past eruptions has shaped human history in countless quiet ways. All of these forms, pahoehoe, pillow, basalt, rhyolite, pumice, obsidian, tuff, are simply different expressions of the same underlying material. Magma, transformed by where and how it cools, becomes the visible variety of volcanic rock that covers so much of the Earth's surface. To pick up a piece of any of them is to hold a small piece of cooled, deep planetary heat. Tonight, somewhere in the world, lava is cooling slowly into one of these forms. Pahoehoe is wrinkling somewhere on Hawaii. Pillow lava is stacking itself somewhere along the mid-Atlantic ridge. AA is grinding gently across the slopes of an active vent. Volcanic ash is drifting on a high-altitude wind, perhaps thousands of kilometers from where it began. The slow, patient transformation of magma into rock is continuing on its own through the night. Let the slow, patient cooling rest gently in your mind. The molten rock of the deep earth becoming the solid stone of the surface, the constant slow conversion that has built so much of the visible world, the patient chemistry of cooling magma doing its work in countless places exactly as it has for billions of years. Let us drift very gently toward the famous mountains of the volcanic world. Among the thousands of volcanoes scattered across the surface of the earth, a small number have become famous. Some are famous for their beauty, some are famous for their size, some are famous for the long histories of human civilization that have grown up around them. Each one is a slow, patient mountain, but each one has gathered its own particular significance over time. Mount Vesuvius on the western coast of Italy is one of the most famous volcanoes in the world. It rises gently above the Bay of Naples, a steep cone visible for many kilometers across the surrounding countryside. The mountain has been part of the Italian landscape for hundreds of thousands of years, and its slopes are covered in vineyards, orchards, and small terraced farms. Vesuvius is best known for the long ago morning when it covered the Roman city of Pompeii in ash, preserving it almost perfectly beneath layers of fine volcanic material. The buried city remained hidden for many centuries until it was rediscovered and slowly excavated. Today, walking through the streets of Pompeii is like walking through a quiet snapshot of an ancient afternoon, frozen in volcanic stillness. Mount Etna, on the eastern coast of Sicily, is the largest active volcano in Europe. It rises more than 3,300 meters above the surrounding plain, dominating the entire eastern part of the island. Etna has been quietly active for hundreds of thousands of years. Its slopes are home to ancient olive groves, vineyards producing distinctive wines, and small towns whose histories stretch back to long before recorded time. Mount Fuji in central Japan is perhaps the most photographed mountain in the world. Its perfectly symmetrical cone, rising more than 3,700 meters above the surrounding plains, has been a sacred mountain in Japanese culture for many centuries. Fuji has been dormant since the early 18th century, standing in calm patience above the changing seasons of Honshu. Fuji has appeared in countless Japanese paintings, poems, and prints over the centuries. The artist Hokusai in the early 19th century made a famous series of woodblock prints called 36 Views of Mount Fuji, in which he depicted the same mountain from many different angles in different seasons under different weather conditions. The mountain became for him a kind of patient anchor against which the changing world could be measured. Krakatoa, in the strait between Java and Sumatra in Indonesia, is famous for the immense activity of 1883. The eruption was so powerful that it was heard nearly 5,000 kilometers away in distant Australia. Most of the original island disappeared beneath the sea. Today, A smaller volcano called Anak Krakatau, meaning child of Krakatoa, slowly grows in the same place, building a new island from the seafloor. Yellowstone in the western United States is one of the largest volcanic features in the world. The wide caldera at its center is roughly 55 kilometers wide by 70 kilometers long. It has been intermittently active for over 2 million years, in a slow rhythm of long, quiet periods separated by occasional larger releases of energy. Today, Yellowstone is a vast, quiet landscape of geothermal pools, hot springs, geysers, and gentle thermal valleys. Mount St. Helens in Washington state became famous in 1980 when the upper part of its cone shifted dramatically and the mountain reshaped itself into the form it now has. Today, the mountain is again quiet. A small lava dome slowly grows in the new crater. The surrounding landscape, once stripped of vegetation, has slowly recovered into a remarkable patchwork of meadows, young forests, and hot mineral lakes. Mauna Loa, on the island of Hawaii, is the largest single mountain on Earth by volume. Its broad shield extends from the summit at 4,169 meters above sea level all the way down to the deep sea floor more than 5,000 meters below. The total height from base to summit exceeds 9,000 meters taller in total relief than Mount Everest. Mauna Loa has been growing patiently for hundreds of thousands of years. Beside Mauna Loa stands Kilauea, one of the most continuously active volcanoes on Earth. For long stretches of recent decades, Kilauea has slowly produced gentle flows of lava that wend their way down toward the sea, occasionally adding new land to the island as they enter the water. The volcano sits at the heart of Hawaii Volcanoes National Park, a place sacred in native Hawaiian tradition. Mount Kilimanjaro in Tanzania is the tallest mountain in Africa. It is a stratovolcano with 3 distinct cones, the highest of which reaches just under 5,900 meters above sea level. Kilimanjaro has been dormant for many thousands of years. Its summit, despite being almost on the equator, is capped with a glacier that has been slowly shrinking over the past century. Cotopaxi in Ecuador is one of the highest active volcanoes in the world, reaching nearly 5,900 meters. Its perfectly symmetrical glacier-capped cone rises above the high Andean plateau, visible for many kilometers in every direction. Cotopaxi has been intermittently active for many centuries with long, quiet stretches between brief reawakenings. Mount Rainier in Washington state is the most prominent peak in the Cascade Range. It rises to 4,392 meters and dominates the skyline of the entire Puget Sound region. Rainier is a classical stratocona with a permanent ice cap supporting some of the largest glaciers in the contiguous United States. The mountain has been mostly quiet for the past 500 years. Mount Erebus in Antarctica is the southernmost active volcano in the world. It rises 3,794 meters above the frozen continent near the McMurdo Research Station on Ross Island. Erebus is unusual in that its summit holds a continuously molten lava lake, one of only a handful of such persistent lakes on Earth. The lake has been active for many decades, slowly bubbling beneath the polar sky. Stromboli in the Mediterranean off the coast of Italy is sometimes called the lighthouse of the Mediterranean. It has been intermittently active for thousands of years, producing small, gentle releases of glowing material from its summit on a roughly continuous basis. The slow, regular activity makes it possible for sailors to see the mountain glowing softly at night from many kilometers away. Mount Tambora in Indonesia was the source of one of the largest volcanic events in recorded history in the early 19th century. The activity was so substantial that fine ash circled the globe and lowered global temperatures slightly for the next year. Today, Tambora is mostly quiet. Its wide caldera holding a small lake within its rim, a reminder of the patient power that lies beneath the surface. Mount Katmai in Alaska sits within Katmai National Park, surrounded by the Valley of 10,000 Smokes, a long valley once filled with countless small geothermal vents that released gentle steam for many years after the last activity. The smokes have mostly faded today, but the valley still holds traces of the patient, slow energy that flowed through it. Mount Bromo on the island of Java in Indonesia sits within an enormous caldera called the Sea of Sand. The active cone of Bromo rises gently from a wide, flat plain of fine volcanic ash that fills the larger caldera. From the rim of the caldera at dawn, the view is famously beautiful, a small dark cone, gentle sulfur clouds drifting upward, and the sun rising slowly over the surrounding mountains. These famous mountains are only a small selection of the thousands of volcanoes around the world. For every well-known peak, there are hundreds of less famous mountains standing in patient quietude, equally interesting to a geologist, equally beautiful to anyone who happens to visit them. Fame is not the measure of significance in the slow geological world. Tonight, all of these famous mountains are at rest, somewhere in the world. Vesuvius is standing quietly above the Bay of Naples. Fuji is reflecting the moonlight from its snowy summit. Kilimanjaro is rising above the dark African plain. Mauna Loa is gently extending out into the Pacific. Erebus is glowing softly at the bottom of the world. Each one is continuing its slow, patient existence, exactly as it has for centuries. There is something steadying in the thought of all these mountains, standing in their many countries, on their many coasts, beneath their many night skies. The world is full of patient volcanoes. Most of them on most nights are simply standing. The slow geological surface of the earth is, in this small way, a quiet companion to all of human history. Let us drift very gently toward the volcanoes that lie hidden beneath the surface of the sea. Most of the volcanoes on Earth are not on land. They are beneath the sea. Beneath the wide, quiet surface of the world's oceans lies a much more active volcanic landscape than anything visible to us above the water. Long chains of underwater mountains, broad fields of glowing vents, and countless small seamounts cover the ocean floor of every basin in the world. The longest mountain range on Earth is not the Andes or the Himalayas. It is the mid-ocean ridge, a continuous underwater chain of volcanic mountains that runs through every ocean basin in the world. The total length is more than 65,000 kilometers, long enough to wrap 1.5 times around the Earth. The mid-ocean ridge is, by far, the largest single geological feature on the planet. The ridge marks the places where two oceanic plates are slowly pulling apart. As they separate, hot mantle rock from below rises into the gap, slowly cooling into new crust along the central seam. The slow upwelling makes the central ridge slightly higher than the surrounding seafloor, and it produces a long line of small underwater volcanoes that runs along its length. The Atlantic Ocean has the most well-studied section of the mid-ocean ridge. The Mid-Atlantic Ridge runs down the center of the Atlantic, from north of Iceland in the Arctic through the equator, and on down to south of Africa near Antarctica. The ridge is the source of the slow widening of the Atlantic. Iceland, which sits directly atop the ridge, is one of the few places where the underwater chain rises above the surface of the sea. Beyond the central ridges, the deep ocean floor is dotted with countless smaller underwater volcanoes called seamounts. A seamount is any underwater mountain that rises at least 1,000 meters above the surrounding seafloor without breaking the ocean surface. Some estimates suggest there may be more than 100,000 seamounts in the world's oceans, far more than the number of land volcanoes by any reasonable count. Many seamounts began as active volcanoes long ago, then went quiet, and have been slowly subsiding into the seafloor ever since. Their tops, once perhaps near the sea surface, have sunk over millions of years to depths of hundreds or thousands of meters. The patient downward drift of old seamounts is one of the slower processes of the ocean basins. Other seamounts are still active. Some are growing slowly toward the surface, layer by layer, as their underlying magma sources continue to feed them. Loihi, off the coast of Hawaii, is one of these. It is a young underwater volcano slowly building itself toward the surface, currently sitting about 900 meters below sea level. In tens of thousands of years, Loihi may break the surface and become the next island in the Hawaiian chain. In the deep, dark waters along the mid-ocean ridge, special volcanic features called hydrothermal vents emerge from the seafloor. These vents are places where seawater has seeped down into the cracks of the crust, been heated by the rock below, and is now returning to the surface as hot mineral-rich water. The water emerges through tall, chimney-like structures built up of dissolved minerals that solidify on contact with the cold sea. The chimneys are remarkable structures. They can grow several meters tall in a single year, building themselves continuously as new minerals settle out of the rising water. Some chimneys are dark and dense, releasing water rich in iron and sulfur. These are called black smokers. Others are paler and lighter, releasing water rich in calcium and barium. These are called white smokers. Each one is a small, slow industrial sculpture, built by the patient chemistry of heated seawater. Around the hydrothermal vents, in water that is far too hot, dark, and chemically extreme for most life forms, an extraordinary set of organisms has evolved. Tube worms, taller than a person, sway gently in the warm currents around the vents. Albino crabs and shrimp creep slowly across the chimneys. Mats of bacteria coat every surface. The community is supported not by sunlight, as nearly all other life on Earth is, but by the chemical energy in the vent water itself. This kind of community, supported by chemistry rather than sunlight, was unknown to science before the late 1970s. Its discovery was one of the great surprises of modern biology. It revealed that life on Earth does not require the sun. Wherever there is energy and water and chemistry, life can take hold. The deep, dark vents of the ocean ridges are home to ecosystems whose existence had not been imagined a few generations ago. The discovery of the vent communities also has implications for the search for life on other worlds. Beneath the icy crust of Jupiter's moon Europa, there is thought to be a deep ocean of liquid water in contact with a rocky seafloor. If hydrothermal vents exist on that seafloor, they might support exactly the same kind of chemistry-based ecosystems we see at the bottom of our own ocean. The deep vent worlds of Earth may be small windows into what may exist elsewhere in the solar system. The slow underwater volcanism of the mid-ocean ridge is constantly producing new oceanic crust. Every centimeter of new seafloor that emerges from the central ridge eventually drifts outward, carried by the slow motion of the plates, until it reaches a subduction zone many millions of years later and begins its slow descent back into the mantle. The entire ocean floor of the world is, in some sense, in slow, patient circulation through the planet. The oldest oceanic crust anywhere in the world is only about 200 million years old. By comparison, some of the oldest rocks on the continents are more than 4 billion years old. The continents are slow, patient archives of deep time. The oceans, by contrast, are constantly being renewed. The seafloor is always young in geological terms because it is always being made and unmade by the slow, patient work of the ridges and the trenches. Beyond the central ridges, in the deep abyssal plains of the ocean, occasional eruptions also occur. Sometimes a new submarine vent opens far from any known volcano, releasing a slow plume of warm water and fine ash for a few months or years before going quiet again. The deep ocean floor is more active than the surface above it, even in places where no surface activity is ever seen. Some submarine eruptions, when they occur in shallower water, can produce floating rafts of pumice that drift across the ocean for thousands of kilometers. The rafts can be enormous, sometimes hundreds of square kilometers in area, made of countless small pieces of light frothy lava that have cooled with bubbles trapped inside. Birds rest on the floating pumice. Marine organisms colonize it. Eventually, after weeks or months, the pumice slowly absorbs water and sinks. Tonight, beneath the wide, quiet surface of every ocean, the underwater volcanoes continue their slow, patient work. The mid-Atlantic ridge is producing new crust. The mid-Pacific seamount chains are slowly subsiding. Loihi is creeping toward the future surface of the sea. Hydrothermal vents are quietly building their chimneys. Tube worms are swaying around them in the warm, dark water. None of this can be seen from above. All of it is continuing, exactly as it has for billions of years. There is something deeply restful in the thought of these quiet underwater worlds, the hidden seamounts in their patient subsidence, the vent communities thriving in total darkness on chemistry alone, the ridges slowly producing new crust beneath kilometers of cold ocean. None of it requires our attention. All of it is part of the slow, ongoing work of the planet, completely indifferent to the world above the water. The deep ocean is, in many ways, the place where Earth's slow geology is most obvious. The seafloor is always changing, always being made and unmade, always breathing in and out at the patient time scale of the planet itself. Beneath every wide, calm surface lies a slow, active world. Let the slow underwater world rest gently in your mind. The ridges and the seamounts and the vents are continuing exactly as they have for billions of years. The deep, dark sea holds their slow, patient work, holds the strange, unimagined ecosystems that have grown up around them. The world is much larger and more active beneath the surface than it ever appears from above. The fish are sleeping above. The vents are working below. The slow, patient work of the ocean continues in countless places all over the dark hemispheres of the world. Let us drift very gently toward the strange phenomenon of hotspots, the volcanoes that appear in the middle of plates far from any boundary. Most volcanoes form along the boundaries between tectonic plates, but a small number form in places that have nothing to do with plate boundaries, far from any ridge, far from any subduction zone, sometimes in the middle of a great oceanic plate or in the deep interior of a continent. These unusual volcanoes are called hotspots, and their origin is one of the more interesting puzzles of modern geology. A hotspot is thought to be the surface expression of a stationary plume of unusually hot rock that rises from deep within the mantle. The plume reaches up from somewhere near the boundary between the lower mantle and the outer core, perhaps 3,000 kilometers below the surface. As the plume reaches the bottom of the crust, it produces magma which slowly works its way upward to the surface above. Because the plume itself stays in roughly the same location for very long periods of time, while the plate above it slowly drifts, hotspots tend to produce long chains of volcanoes. The active volcano sits over the plume. Older volcanoes, no longer connected to the plume, drift slowly away with the plate, leaving behind a visible track of extinct cones that becomes older with distance from the active vent. The Hawaiian hotspot is the most famous example. The Hawaiian Islands stretch across more than 2,000 kilometers of the Pacific Ocean, with the largest and most active island, Hawaii itself, at the southeastern end of the chain. As you move northwestward along the chain, the islands become older and smaller, gradually eroded by wind and rain into low submerged seamounts. Beyond the visible Hawaiian Islands, the chain continues underwater as the Emperor Seamount Chain, a long line of submerged ancient volcanoes that runs all the way north toward the Aleutian Trench off Alaska. The oldest seamounts in the Emperor Chain are about 80 million years old. The youngest seamount, Loihi, is still growing today off the southeast coast of Hawaii. The chain is a record of 80 million years of patient, slow drift over a stationary, deep plume. There is even a small bend in the Hawaiian Emperor Chain, where the alignment changes direction sharply about 43 million years ago. The bend is thought to record the moment when the Pacific Plate changed its direction of motion. The slow, patient hotspot recorded the change in the geometry of the chain it was building, like a long needle quietly tracing the slow motion of a great floating sheet of crust. Iceland sits over a different hotspot, one that happens to coincide with the mid-Atlantic ridge. The combination of a divergent plate boundary and a stationary mantle plume makes Iceland one of the most geologically active places on Earth above sea level. Iceland would not exist as a substantial above-water landmass without the unusual coincidence. The country owes its very being to the slow upward push of deep mantle rock. Yellowstone in the western United States sits over yet another hotspot. The Yellowstone hotspot has been active for at least 17 million years. As the North American plate has slowly drifted southwestward over the plume, the hotspot has produced a long track of older calderas across what is now eastern Idaho and Wyoming. The current caldera at Yellowstone is simply the most recent stop on the long, slow journey of the plate above the plume. The Galapagos Islands sit over a hotspot in the eastern Pacific, just off the coast of Ecuador. The chain of small volcanic islands that makes up the archipelago has produced the unique ecosystems that famously inspired Charles Darwin's thinking about evolution. Each island has its own slightly different conditions, depending on its age and elevation, and each one supports its own slightly different community of plants and animals. The Réunion hotspot in the Indian Ocean sits beneath the small island of Réunion off the eastern coast of Madagascar. The Piton de la Fournaise on Réunion is one of the most consistently active volcanoes in the world, producing gentle, slow flows on a roughly continuous basis. The Réunion hotspot also has a much older track that extends northward across the Indian Ocean, including the Maldive Ridge and the Deccan Plateau of India. The Deccan Traps of India are the eroded remains of an enormous outpouring of basalt that occurred around 66 million years ago, when the Réunion hotspot lay beneath what is now western India. Over a few 100,000 years, the hotspot produced layer upon layer of basalt across an area larger than France, building a thick volcanic plateau that still covers much of central India today. The hotspot then drifted away, leaving the Deccan Plateau behind as a long, quiet record. The world has somewhere between 40 and 50 currently active hotspots scattered across the oceans and continents. Some are very active with frequent volcanism, some are quiet, with eruptions only every few thousand years. Some, like the Tristan da Cunha hotspot in the South Atlantic, or the Easter Island hotspot in the southeastern Pacific, have produced small, isolated chains of volcanic islands far from any other land. Hotspots are thought to be the source of some of the largest single volcanic outpourings in the geological record. From time to time, in deep history, a hotspot has produced what geologists call a large igneous province, a vast outpouring of basalt that covers an area of millions of square kilometers and represents tens or hundreds of thousands of years of slow, continuous activity. The Deccan Traps are one example. The Siberian Traps are another. The Columbia River basalts of the western United States are a third. These large igneous provinces are deeply important to the history of the Earth. Some of the largest of them coincide in time with major shifts in the global climate and the global biosphere. The slow gases released from such enormous outpourings appear to have changed the chemistry of the atmosphere on geological timescales, contributing to some of the great transitions in the history of life on Earth. The deep mantle plumes themselves are difficult to study directly. Most of what geologists know about them comes from indirect evidence: the patterns of hotspot tracks across the surface, the chemistry of the rocks they produce, the seismic signals that pass through them deep beneath the surface. Recent imaging has revealed that some plumes appear to be rooted near the boundary between the mantle and the core, 3,000 kilometers down. Others may be shallower, originating in the upper mantle. There are still many open questions about hotspots. Why do they appear where they do? Why do some last for hundreds of millions of years while others last only a few million? How exactly do the plumes form deep within the mantle? Geologists continue to study them, slowly building a clearer picture of the deep processes that bring the inner heat of the Earth up to the surface in unusual places. There is something pleasingly mysterious about the existence of hotspots. They do not fit the neat pattern of plate boundaries. They appear in unexpected places. They sometimes vanish without warning after millions of years of activity. They sometimes appear in places that had been quiet for hundreds of millions of years. The hotspots remind us that the slow inner Earth is still capable of surprises. The Hawaiian hotspot will continue slowly for many millions of years to come. The Pacific Plate will continue to drift northwestward over the plume, and new islands will continue to be built at the southeastern end of the chain. Loihi will eventually break the surface and become a new island, joining its 8 elder siblings in the Hawaiian archipelago. After that, perhaps a million years later, yet another new island may begin to rise from the seafloor. Yellowstone, similarly, will continue. The North American plate will continue to drift southwestward, and the hotspot will eventually move beneath what is now eastern Wyoming or Montana. New calderas may form there in some distant future, while the current Yellowstone caldera slowly cools and erodes into a long, quiet basin in the Rockies. Tonight, the deep mantle plumes continue their slow, patient work. The Hawaiian plume is still feeding Mauna Loa and Kilauea. The Iceland plume is still bringing fresh basalt up beneath the country. The Yellowstone plume is still warming the geysers and hot springs of the Great Caldera. None of these processes can be seen directly. All of them are continuing, exactly as they have for many millions of years. There is something companionable in the slow, deep work of these hidden plumes. They have been there for far longer than any human civilization. They will continue for far longer still. The slow upward push of deep mantle rock is one of the most patient processes on Earth, and it has been quietly shaping the surface of the world for billions of years. Let us drift very gently toward the surface wonders that volcanoes produce. The geysers, the hot springs, the gentle thermal pools. Around the bases of many volcanoes, where the deep heat of the Earth comes close to the surface, water heated by the rock below produces some of the most beautiful features on the planet. Hot springs, geysers, fumaroles, mineral terraces, blue thermal lagoons. These are the gentle surface expressions of the slow, patient warmth of the inner Earth, made visible in steam and color. A hot spring is simply a place where water heated underground emerges naturally at the surface. The water has seeped down through cracks in the rock, sometimes hundreds or thousands of meters deep, where it has been warmed by contact with hot rock near a magma chamber. As the warmed water rises again, often along a different fracture system, it emerges from the ground gently and slowly, sometimes producing pools of remarkable color. Hot springs occur all over the world, in every part of every continent that has any volcanic history at all. The most famous concentrations are in Yellowstone in the United States, in the geothermal regions of Iceland, in the spa towns of Central Europe, in the volcanic highlands of New Zealand, and in many parts of Japan. Each region has its own characteristic style of hot spring, shaped by the local chemistry of the rock and the local temperature of the underground heat. The colors of hot springs are often spectacular. Some are deep blue, the color of pure water reflecting deep light. Some are pale turquoise, like glacial meltwater. Some are bright orange or yellow or green, colored by mineral compounds dissolved in the water or by mats of heat-loving microorganisms living in the warm pool. The Grand Prismatic Spring in Yellowstone, with its rings of red, orange, yellow, and blue, is one of the most colorful natural features in the world. The colors at Grand Prismatic come from microbial communities around the central pool where the water is hottest. Only a few species of bacteria can survive, producing pale yellow and white mats. Further out, where the water is cooler, more species can live, producing the orange and brown rings. The deep blue center is simply the color of clear hot water reflecting the sky. The whole pool is a slow-living mosaic. Geyser is a special kind of hot spring that periodically erupts a column of water and steam into the air. Geysers are quite rare. In all the world, there are probably fewer than 1,000 active geysers, and most of them are concentrated in just a few regions. Yellowstone has about half of the world's geysers. Iceland has many of the rest. New Zealand and Kamchatka have smaller concentrations. A geyser works because of an unusual underground geometry. Beneath the surface, narrow, constricted plumbing connects a deep chamber of water to the surface vent. As the deep water heats, it tries to expand into steam, but the constriction at the top traps it. Pressure builds slowly. Eventually, when enough steam has formed, the trapped water above is pushed up and out of the vent in a slow rising column. Once the pressure releases, the cycle slowly begins again. Old Faithful in Yellowstone is the most famous geyser in the world. It is famous because of its predictable cycle. For many decades, it has produced a gentle column of water and steam, roughly every 90 minutes, almost exactly on schedule. Visitors gather at the boardwalks around it, watch it slowly build, watch it slowly release, and then disperse to watch other features in the park. Old Faithful is a slow, patient, natural metronome. In Iceland, the original geyser from which all geysers take their name has been mostly quiet for the past 100 years. Beside it, however, the smaller Strucker erupts every few minutes, producing a tall, slim column of water and steam in a slow rhythm that has been continuous since the 18th century. The geyser region of Iceland is, in some sense, the original namesake landscape, the place from which a whole category of natural feature took its name. Fumarolas are openings in the ground where steam and gases emerge without much liquid water. The steam is heated by the rock below and rises gently through narrow cracks in the surface. Fumarolas often form in groups around the edges of active volcanic regions, producing slow plumes of mist that drift gently into the surrounding air. Some fumarolas are colored by the minerals dissolved in their gases: yellow sulfur, orange iron oxides, white salt. Mineral terraces form when hot springs gradually deposit minerals from their water onto the surrounding ground. Over thousands of years, the slow deposits build up into elaborate stepped terraces of pale stone, each terrace holding a small shallow pool. Mammoth hot springs in Yellowstone, Pamukkale in Turkey, and the Huanglong terraces in China are among the most famous examples. Each terrace system is a slow architectural sculpture built by patient water. Pamukkale, whose name means cotton castle in Turkish, is one of the most striking mineral terrace systems in the world. The white limestone terraces formed by calcium-rich water flowing down a hillside for thousands of years look from a distance like a frozen waterfall of pale stone. The thermal pools held in the terraces are warm and gentle, and they have been used for bathing for many centuries. In Iceland, the Blue Lagoon is one of the most famous geothermal pools in the world. Its milky blue water comes from the hot fluid emerging from the ground nearby, rich in dissolved silica that gives the water its characteristic pale color. The lagoon sits in a black volcanic landscape surrounded by ancient lava fields, with low steam drifting gently across its surface in the cool air. In Japan, hot springs are called onsen. They are deeply embedded in Japanese culture, with a tradition of bathing that stretches back over 1,000 years. Many onsen are quietly tucked into mountain valleys, surrounded by forests of cedar and pine. The water emerges from deep within the volcanic rocks of the islands, slowly warmed by the patient inner heat of the earth beneath. In New Zealand, the Champagne Pool in the Waiotapu thermal area sits within a wide caldera, its surface bubbling gently with carbon dioxide that gives the pool its name. The water around the edges is bright orange, colored by deposits of antimony and arsenic minerals. The pool has been bubbling slowly for hundreds of years, a gentle, continuous reminder of the deep volcanic system beneath. Beyond their visual beauty, geothermal features have practical importance as well. Many regions with significant geothermal activity now generate substantial portions of their electricity from steam produced by the hot rocks beneath. Iceland gets nearly all of its heating and most of its electricity from geothermal sources. Italy, the Philippines, Indonesia, Kenya, and parts of California also generate significant geothermal power. The slow inner heat of the Earth, in this small way, has become part of the modern energy of certain countries. Geothermal heat also supports unique ecosystems. The microbial communities of hot springs include some of the oldest and most chemically interesting forms of life on Earth. Some of the bacteria found in hot springs can tolerate temperatures of over 100 degrees Celsius, temperatures that would kill nearly any other organism. The study of these extreme microbes has revealed important truths about the limits and origins of life itself. Some scientists believe that life on Earth may have first arisen near hot springs or hydrothermal vents, where the chemistry of warm water and dissolved minerals could have allowed the slow assembly of the first organic compounds. If this is correct, the modern hot springs of Yellowstone, Iceland, and elsewhere may be quiet living echoes of the very landscape in which life on our planet first began. Tonight, all over the world, the geothermal wonders are continuing their slow, patient work. Steam is rising gently from countless fumaroles, hot springs are slowly bubbling, geysers are building toward their next quiet eruptions. Mineral terraces are slowly adding new layers of stone. The slow surface expression of the deep inner heat of the Earth is continuing, exactly as it has for millions of years. There is something deeply restful in the thought of these gentle steaming worlds. The hot springs and geysers and fumaroles are not violent or threatening. They are quiet expressions of slow inner warmth, made visible in patient, slow ways. They have been with us for as long as there have been people to bathe in them, and they will continue for far longer still. Let the slow, gentle steam rest in your mind. The hot springs are continuing. The geysers are slowly building. The mineral terraces are growing, layer by layer, the way they have for thousands of years. The inner heat of the earth is reaching the surface in countless gentle places, exactly as it should all over the patient world. Let us drift very gently toward the slow birth of new land from beneath the sea. Some of the slowest and most patient processes on Earth involve the gradual creation of new land from the sea. The volcanic islands of the world, every one of them, were once nothing more than slow upward growths from the deep seafloor, building themselves quietly over thousands or millions of years until they finally broke the surface and began to gather a small, thin atmosphere of life around themselves. In November of 1963, a small fishing boat off the southern coast of Iceland reported an unusual sight, a column of dark smoke rising from the open sea. Within hours, the smoke had grown into a vast plume, and a small new island had begun to push its way above the waves. The new island was given the name Surtsey after Surtur, a fire being from Old Norse mythology. Surtsey continued to grow for the next 4 years. By the time the activity finally ended in 1967, the new island was about 2.5 square kilometers in area, with a small low cone of fresh black basalt and ash. From the moment of its birth, Surtsey was placed under careful scientific protection. No human visitors are allowed except for a small number of authorized researchers, and even they must be careful not to introduce any seeds or microbes from outside. In the years since, Surtsey has slowly become a living laboratory for the study of how life colonizes new land. The first organisms to arrive were bacteria, fungi, and algae. Then came mosses and lichens, then small flowering plants, carried in on the wind or by occasional birds. Then nesting seabirds, which fertilized the soil with their droppings, allowing more substantial vegetation to take hold. Today, Surtsey supports several dozen species of plants, dozens of species of birds, many species of insects, and a slow-growing community of marine life around its underwater base. The island still erodes slowly into the sea around its edges, but its central cone is stable, protected by a thick layer of harder basalt. Surtsey is, in some sense, a small living textbook of the slow biological colonization of new volcanic land. The Hawaiian Islands are perhaps the largest example of new land slowly born from beneath the sea. The Big Island of Hawaii, the youngest of the visible islands, is still actively growing along its southeastern coast, where slow lava flows from Kilauea occasionally reach the ocean and add small new sections of dark land to the existing shore. Each new flow that reaches the sea is a slow, patient extension of the island, layer by layer, year by year. Beneath the southeast coast of Hawaii, the underwater volcano Loihi is slowly building toward the future surface of the sea. Loihi has been growing patiently for many tens of thousands of years, and it currently sits about 900 meters below sea level. In perhaps another tens of thousands of years, it will rise above the waves and begin its existence as a new Hawaiian island, the ninth in the chain. Loihi will spend its first thousands of years above the surface as a small bare cone, similar in many ways to Surtsey. Slowly, life will arrive, first the simplest organisms, then more complex plants and animals. Birds will nest. Marine creatures will colonize the shallows around its edges. After many thousands of years, Loihi will be a small green island in the chain, and its older sibling, the Big Island, will have begun its own slow journey toward eventual erosion and submersion. In some ways, every island in the world began its existence as a small bare volcanic cone. Iceland, the British Isles, the Galapagos, the Canaries, the Azores, the Aleutians, Japan, Indonesia, the Philippines, Madagascar, New Zealand, the South Pacific archipelagos, all of them have at least some component of volcanic origin. The slow process of new land emerging from beneath the sea has been going on in many places for as long as there have been oceans. Even some of the larger land masses we now call continents began as smaller volcanic terrains, slowly accreting onto each other and onto older continental cores over many hundreds of millions of years. Western North America in particular was built up over the past billion years from a long series of volcanic island arcs that were slowly carried into the continental margin and pasted onto the existing edge. The continents themselves are, in some sense, slow, patient collages of much older volcanic islands. Volcanic islands also occasionally appear far from any plate boundary, in the middle of an ocean basin. The Hawaiian Islands and the Galapagos are the most famous examples, but there are also the Cape Verde Islands in the Atlantic, the Crozet and Kerguelen archipelagos in the Indian Ocean, and Easter Island in the southeastern Pacific. Each is a small, slow expression of a deep mantle plume, slowly building new land out of the deep seafloor over many millions of years. In some places, new volcanic islands appear, persist for some time, and then slowly disappear again. The North Atlantic, for example, has produced several small ephemeral islands over the past few centuries, none of which lasted more than a few decades before being eroded back into the sea. The slow back and forth of building and unbuilding is part of the patient story of every active volcanic region. Once new volcanic land has emerged and stabilized, the process of soil formation begins. Bare volcanic rock is hostile to most plants. It has few nutrients, holds little water, and weathers slowly. But over thousands of years, the slow action of wind, rain, lichen, and microbial decay gradually breaks down the rock and creates the first thin soils. Once soil exists, more substantial plants can take hold, and the slow process of building a true ecosystem can begin. Volcanic soils, once formed, are remarkably fertile. They are rich in essential minerals, well-drained, and good at holding moisture in the right amounts. Many of the most productive agricultural regions in the world are built on volcanic soil. The terraced rice fields of Java, the vineyards of Etna, the coffee plantations of Hawaii and Costa Rica, the apple orchards of Mount Hood, all of them grow in soil that came originally from slow, ancient volcanic outpourings. Around the bases of older volcanic islands, beneath the warm, shallow seas, coral reefs slowly grow. The reefs colonize the gentle slopes of the underwater volcanic flanks, building their slow-living structures over thousands of years. As the volcanic island slowly subsides, the reef can continue growing upward, sometimes producing the ring-shaped atolls so characteristic of the Pacific Ocean. The atoll is, in some sense, the underwater shadow of an older volcanic island that has long since sunk away. In the very long run, every volcanic island will erode and subside back into the sea. The slow forces of wind, rain, and waves wear down the cone. The slow cooling of the underlying volcanic rock causes the island to slowly sink. After many millions of years, even the largest volcanic island becomes a low submerged seamount, eventually no longer breaking the surface at all. The sea slowly takes back what the volcanoes have slowly given. This long cycle of birth and slow disappearance has been going on for as long as there have been oceans on Earth. New land emerges, new ecosystems develop, the land slowly erodes, the sea slowly takes it back. The cycle has produced and unproduced countless small islands over the long history of the planet, in countless ocean basins, in every era. The slow circulation of land and sea is one of the great patient rhythms of our world. Tonight, somewhere in the world, a new volcanic island is growing patiently beneath the sea. Loihi is still slowly building. New seamounts are forming along the mid-ocean ridges. Small flows are slowly extending the edges of existing islands. The patient creation of new land is continuing, exactly as it has for billions of years in dozens of quiet places around the world. There is something deeply hopeful in the slow creation of new land. The world is not finished. New places are still being made, new possibilities for ecosystems, for life, for slow patient development are still emerging beneath the surface of the sea. The Earth is, in this small way, still a young planet, one that is constantly making more of itself. Let the slow, patient creation of new land rest gently in your mind. The Earth is still building itself, slowly in countless small ways. Beneath the wide, quiet surface of the sea, there is no hurry. There is no end. The world is patient, and it is slowly, quietly becoming more. Let us drift very gently toward the unique forms of life that have grown up around the slow heat of volcanoes. Wherever there is volcanic activity on Earth, there is somehow life. Even in the harshest volcanic environments, in scalding hot springs on the steep flanks of recently cooled lava, around the dark vents of the deep ocean floor somewhere, some form of life has slowly evolved to make a home there. Volcanoes, far from being barren, are some of the most biologically interesting landscapes on the planet. The first life to colonize fresh volcanic rock is microscopic. Bacteria, fungi, and algae arrive on the wind or in dust, settling into the small cracks and pores of the cooling stone. They are not many at first. They are barely visible. But they begin slowly the work of breaking down the rock, releasing nutrients, and building the first faint film of organic matter that will allow more substantial life to follow. Lichens are often the next arrivals. Lichens are remarkable organisms, partnerships between fungi and algae that can grow on bare stone where almost nothing else can survive. Lichens slowly etch into the rock surface, breaking it down further, while their living tissues hold moisture and accumulate organic material. Patches of pale gray or yellow lichen on cooled lava may seem unimpressive, but they are doing the slow work of preparing the surface for everything that will follow. Mosses come next, where conditions allow. Mosses can take hold in places where other plants cannot, especially in the cool, moist conditions of higher elevations or shaded crevices. A small cushion of green moss on a cooled lava flow can persist and slowly expand for many years, gathering organic matter beneath itself, eventually creating a small thin patch of soil where seeds from more substantial plants might take hold. Once thin soils have formed, the first vascular plants arrive. On Hawaii, the native ohia tree, with its small bright red blossoms, is one of the first plants to colonize fresh lava flows. Its seeds blow onto the dark, cooled stone, and the young trees grow roots that work their way slowly into the cracks of the volcanic rock. Over decades, the ohia builds a slow forest where there was once only bare basalt. In Iceland, the first substantial plants to colonize new lava are typically grasses and small wildflowers, adapted to the cold, windy conditions of the high latitudes. The slow buildup of grass turf on Icelandic lava flows can take many decades, but eventually the rough black surface of the lava becomes covered in soft green meadows that look almost as if they had always been there. On the slopes of older volcanoes, where soil has had thousands of years to develop, much more substantial vegetation can grow. The volcanic islands of Indonesia and the Philippines are covered in dense tropical forests that thrive on the rich volcanic soil. The slopes of Mount Etna in Sicily support ancient olive groves and vineyards. The flanks of Mount Fuji are covered in dense forests of beech and Japanese cedar. In the long shadow of Mount Etna, vineyards have produced distinctive wines for thousands of years. The volcanic soil, rich in minerals and well-drained, gives the wines a particular character that they cannot get from any other terrain. Etna wines have been celebrated since ancient Roman times. The slow, patient mountain has provided, in this small way, a kind of gift to the human cultures that have lived around it. Around the edges of hot springs, where the water is warm but not too hot for life, certain heat-loving bacteria and microbial mats thrive. These thermophiles have adapted to temperatures that would be lethal to most organisms, and their study has revealed remarkable details about the limits of life. Some thermophiles can survive at temperatures of over 100 degrees Celsius, near the boiling point of water. Even more remarkable is the life that thrives around hydrothermal vents on the deep sea floor. The communities found there, tube worms, white crabs, blind shrimp, mats of chemosynthetic bacteria, were entirely unknown to science until the late 1970s. They live in total darkness, in water that is far too hot, chemically extreme, and nutrient poor for most life forms. They survive on the chemical energy in the vent fluids alone. The discovery of these vent communities transformed our understanding of where life can exist. Before the discovery, it had been assumed that all life on Earth ultimately depended on sunlight, captured by photosynthesis at the surface, and passed up through food chains. The vent communities revealed that life can be supported by chemistry alone, in places that have never seen sunlight in their entire existence. The deep ocean is, in this way, a separate biological world. Volcanic islands often develop unique ecosystems with species found nowhere else in the world. The Galapagos archipelago is the most famous example. Each volcanic island in the chain has its own slightly different conditions, and over many generations the same ancestral species evolved in slightly different ways on different islands. The result is the rich biodiversity that famously inspired Charles Darwin in the early 19th century. The Hawaiian Islands also support a remarkable number of unique species. Plants and animals that arrived long ago, sometimes carried thousands of kilometers across the open Pacific, slowly evolved in isolation into many distinct species. The Hawaiian honeycreeper birds, the silversword plants of Haleakala, the unique Hawaiian fruit flies, all are the slow biological harvest of millions of years of life developing on isolated volcanic islands. The Galapagos finches, which Darwin studied carefully during his visit in 1835, were one of the key sources of insight that led him toward his theory of evolution by natural selection. Each finch species had a slightly different beak, adapted to the slightly different food sources of its particular island. The slow, patient working of evolution on the slow, patient surface of volcanic islands helped to shape one of the most important scientific ideas of modern times. Around the bases of underwater volcanoes, in the warm, shallow waters of tropical seas, coral reefs slowly grow. Many of the most spectacular reef ecosystems in the world are built on the slowly subsiding flanks of older volcanic islands. The coral animals slowly add their calcium skeletons year by year, building the slow-living structure that will support thousands of other species. The reefs are, in some sense, the underwater forests that grow on the slow biological inheritance of volcanic islands. On the cooler, high slopes of large stratocones, distinct ecosystems develop in the layered climate zones. Mount Kilimanjaro in Tanzania is famous for its layered ecosystems: tropical farmland at the base, dense forest above, then heath, then alpine meadow, then bare rock and ice at the summit. Each zone has its own community of plants and animals, all stacked vertically on the same patient mountain. The patient, slow ecosystems of older volcanic islands often persist for many millions of years, slowly evolving as their islands age. Some species end up isolated as their islands subside back beneath the sea, and their lineages eventually disappear. Some species manage to spread to new islands as they emerge, carrying their evolutionary inheritance forward into new chapters of life. The slow rise and fall of volcanic islands is, in some sense, a kind of slow, patient incubator for biodiversity. Tonight, all over the world, life around volcanoes is continuing its slow, patient existence. Lichens are slowly growing on cooled lava in Hawaii. Vineyards are sleeping on the slopes of Etna. Tube worms are swaying around hydrothermal vents in the deep Pacific. Honeycreepers are roosting in mountain forests on the high islands. Coral reefs are slowly building their living structures around the bases of subsiding volcanic islands. The slow biological wealth of the volcanic world is at rest, exactly as it should be. There is something deeply moving in the thought that life finds a way to thrive even in the harshest of volcanic settings. The bare, cooling lava of Surtsey is slowly becoming a small green island. The deep, dark vents of the mid-ocean ridges are home to ecosystems unlike anything else on Earth. The slow, patient creativity of life, working alongside the slow, patient creativity of the Earth, has produced an enormous variety of living worlds in places that might have seemed inhospitable. Let the slow, patient life of the volcanic world rest gently in your mind. The lichens are slowly etching the rock. The reefs are slowly building their living structures. The deep vent communities are continuing their dark, patient existence. All of life in all of its forms is continuing its slow work, exactly as it has for billions of years all over the soft, patient world. Let us drift very gently toward the volcanic worlds of other planets, the slow, distant cousins of our own volcanic Earth. Earth is not the only volcanic world in our solar system. Volcanoes in many forms exist on a number of other planets and moons. Some of those distant volcanoes are larger than anything on Earth. Some are stranger than we could have imagined. Some erupt not lava but ice. The patient, slow geology of volcanism, it turns out, is a feature of many worlds, not just our own. Mars, our closest planetary neighbor, is home to the largest known volcano in the solar system. Olympus Mons rises about 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. Its base is 600 kilometers across, roughly the size of the entire state of Arizona. From the air, if there were any air to fly through, Olympus Mons would not look like a mountain at all. It would look like a vast, gentle swelling of the Martian landscape, far too wide to perceive as a single peak. Olympus Mons is a shield volcano, similar in basic form to Mauna Loa on Earth, but vastly larger. Its slopes rise at a very gentle angle of only about 5 degrees. The summit holds a complex caldera made up of several overlapping collapse pits. The whole structure was built up over billions of years by countless slow flows of basaltic lava emerging from a single long-lived hotspot beneath the Martian crust. Mars has several other large shield volcanoes besides Olympus. The 3 Tharsis Montes, Arzia Mons, Pavonis Mons, and Ascraeus Mons, rise in a long line across the Tharsis bulge of the Martian surface. Each of them is comparable in size to the largest volcanoes on Earth. The Tharsis region as a whole, including Olympus Mons, contains the largest concentration of volcanic mass on any rocky planet in the solar system. Mars is, in some ways, a frozen volcanic world. Most of its volcanoes appear to have gone extinct hundreds of millions or billions of years ago. The Martian crust does not have the active plate tectonics of Earth, so the slow drift that would carry old volcanoes away from a hotspot does not occur. Instead, the same plume can keep building the same volcano for vast periods of time, producing structures of extraordinary size like Olympus Mons. Beyond Mars, the next major volcanic world is Io, the innermost of the 4 large moons of Jupiter. Io is the most volcanically active body in the solar system. Its surface is covered in hundreds of active volcanoes, producing slow, patient activity at any given moment somewhere on the moon. Io's volcanism is so active that the moon's surface is constantly being resurfaced. There are essentially no impact craters visible on Io, because they are all covered over by fresh volcanic material faster than they can accumulate. Io's volcanism is driven by an unusual energy source. The moon orbits Jupiter in an elliptical path, and the changing distance from the giant planet causes the moon's interior to flex slightly with each orbit. The flexing produces enormous tidal heating in the rocky interior, generating heat that drives the relentless volcanic activity. Io is in some sense being slowly squeezed and released by Jupiter, generation after generation, producing a constantly molten interior. The lava that erupts from Io's volcanoes is unusual. Some flows appear to be similar to terrestrial basalt. Others are made of molten sulfur, which is bright yellow when liquid and turns various shades of red and orange as it cools. The mixed surface of Io is a remarkable patchwork of these colors: yellow sulfur plains, white sulfur dioxide frost, dark silicate flows, and the slowly fading colors of older deposits. Io's volcanoes can produce plumes that rise hundreds of kilometers above the surface, far above the Moon's thin sulfur atmosphere. The plumes form because of the low gravity and the absence of any substantial atmosphere. The eruptions look like slow umbrellas of dust and gas opening above the surface, drifting outward and slowly settling back down across the colorful landscape. Venus, our other planetary neighbor, also has substantial volcanic terrain. The surface of Venus is covered in volcanic plains, lava channels, and many thousands of small volcanic structures, including some unique features called pancake domes, broad, flat, circular volcanic structures with steep sides and very flat tops. Venus has more volcanoes by count than any other rocky planet in the solar system, although most of them appear to be currently dormant. The Venusian atmosphere is so thick and chemically extreme that the surface temperature is nearly 500 degrees Celsius, hot enough to melt lead. The slow, active volcanism on Venus has, over billions of years, produced a thick blanket of greenhouse gases that trap solar heat at the surface. The result is a planet very different from Earth, despite being roughly the same size and composition. Recent observations suggest that some of Venus's volcanoes may still be active, slowly producing fresh flows in the present day. The detection has been difficult because the thick clouds of Venus block direct view of the surface, but radar mapping from spacecraft has revealed gradual changes that look very much like fresh volcanic activity. Venus, it seems, is not a dead world. It is simply a hidden one. Mercury, the innermost planet, also shows clear evidence of past volcanic activity. Its surface is covered in vast plains of volcanic basalt, similar to the Maria of our own Moon. Most of Mercury's volcanism appears to have ended billions of years ago, leaving a quiet, ancient volcanic surface that has barely changed since. Our own Moon was once a volcanic world. The dark patches visible on the Moon's near side, the so-called Maria, Latin for seas, are vast ancient lava plains that formed billions of years ago when the Moon was still warm enough to support active volcanism. Today, the Moon is geologically quiet. Its small interior has cooled significantly, and there has been no major volcanic activity for billions of years. The Maria stand as a slow, patient record of a much earlier active phase. In the outer solar system, beyond the asteroid belt, an entirely different kind of volcanism appears. Several of the icy moons of Jupiter, Saturn, Uranus, and Neptune show evidence of cryovolcanism, volcanism in which the molten material is not silicate rock, but liquid water mixed with ammonia and other compounds erupting from a much colder interior. The cryovolcanoes produce slow plumes of vapor and slush rather than glowing lava. Enceladus, a small icy moon of Saturn, is famous for the geyser-like plumes that rise from its south polar region. The plumes are made of water vapor and ice particles ejected from a liquid water ocean beneath the moon's icy crust. The plumes can extend hundreds of kilometers above the moon's surface. Some of the material falls back. Some of it escapes into space, contributing to one of Saturn's outer rings. Triton, the largest moon of Neptune, also shows evidence of cryovolcanic activity. Spacecraft images have revealed dark streaks across its icy surface that may be the deposits from slow plumes of nitrogen and dust erupted from the interior. Triton is one of the coldest worlds in the solar system, with surface temperatures around -230 degrees Celsius. Even in such cold conditions, slow volcanic processes continue. Pluto, that distant small world at the edge of the solar system, also shows evidence of recent or possibly ongoing cryovolcanic activity. Spacecraft images have revealed unusual features that look very much like ice volcanoes, possibly produced by slow upwelling of slushy water-ammonium mixtures from beneath the surface. Pluto, despite being far colder than any of its more famous siblings, is not a dead world. Looking across all of these distant worlds, we see that volcanism is a remarkably general phenomenon. Wherever there is a planet or moon with internal heat, whether from primordial warmth, from radioactive decay, or from tidal flexing, some form of volcanism eventually appears at the surface. The materials may differ, the forms may differ, but the basic process, slow internal heat, finding its way to the surface, is much the same. Tonight, while you rest, the volcanic moons of the outer planets are continuing their slow work. Io is producing its constant patchwork of sulfur and silicate flows. Enceladus is releasing its slow, icy plumes into space. Triton is quietly streaking its surface with cryovolcanic deposits. Olympus Mons stands silent on Mars under a thin pink sky. The Venusian volcanoes are slowly working beneath their thick clouds. The whole solar system is, in some small way, a slowly active volcanic place. There is something deeply expanding in the thought that our own volcanic Earth is not alone. Other worlds are doing similar slow work in their own ways, in their own conditions. The patient processes that built our mountains and shaped our oceans are, in some form, at work elsewhere too. Volcanism is, in a quiet way, a kind of common language of rocky and icy planets across our small corner of space. Let the distant volcanic worlds rest gently in your mind. They are continuing their slow work far away, in the cold, dark spaces between the stars. They have been doing so for billions of years. They will continue exactly as they have for billions more. Let us drift very gently toward the closing of our slow journey through the volcanic world. Thank you for spending this night with the Circadian Institute. If this journey helped you rest, please consider subscribing. It allows us to keep building these slow, deep visits to the quieter places of the slow volcanic world. New videos arrive each week, always at this same patient pace, always meant for your sleep. The journey we have taken tonight slowly through the patient volcanic story of our planet has reached its quiet conclusion. We have visited the glowing inner core, the slow drifting plates, the long ring of fire around the Pacific, the architecture of individual volcanoes, the many shapes they take, the slow chemistry of magma and lava, the famous mountains of the world, the hidden underwater volcanoes, the deep mantled plumes that produce hotspots, the gentle geothermal wonders, the slow birth of new land, the rich lift that has grown up around volcanoes, and the volcanic worlds of distant planets and moons. Each chapter has been a small window into the slow, patient story of the volcanic Earth. There is much more that we could have considered. There is much more that geologists are still discovering. The slow inner Earth is still revealing its secrets, gradually, year by year, as new instruments and new methods allow us to look more deeply into its hidden structure. The journey has been slow on purpose. The Earth itself moves slowly. The patient inner mantle moves slowly. The plates drift slowly. The volcanoes build slowly. There has been no hurry, and there is no hurry now. Whatever you have absorbed, whatever you have not absorbed, whatever you have heard, and whatever you have drifted past, all of it is exactly right. The night has been holding the journey for you. As we close, let yourself rest. Let the bed hold you. Let the pillow hold your head. Let the breath continue on its own, without your supervision. The work of the night, like the work of the earth, is being done without your effort. You do not need to participate. You only need to allow. The volcanoes in countless places around the world are still standing in their patient quiet. The hot springs are still steaming. The geysers are slowly building toward their next gentle releases. The plates are slowly drifting beneath the dark hemispheres of the world. The slow inner mantle is still circulating. All of it is happening exactly as it should on the patient, slow time scale of the planet itself. Somewhere, Mauna Loa is standing quietly above the dark Pacific. Somewhere, Mount Fuji is reflecting the moonlight from its snowy summit. Somewhere, Kilimanjaro is rising above the dark African plain. Somewhere, Mount Erebus is glowing softly at the bottom of the world. Each one is a small living link in the long, slow story of the volcanic Earth. Somewhere, the mid-Atlantic ridge is producing new crust at the bottom of the deep Atlantic. Somewhere, hydrothermal vents are quietly building their chimneys in the dark abyss. Somewhere, Loihi is slowly growing toward the future surface of the sea. Somewhere, the inner core is slowly crystallizing under enormous pressure, each one a small ongoing piece of the slow planetary story. Far above the dark surface of the Earth, on other worlds, distant volcanic processes are also continuing. Olympus Mons stands silent under a thin Martian sky. Io is producing its constant patchwork of yellow sulfur. Enceladus is releasing its slow, icy plumes into space. Triton is quietly streaking its surface with cryovolcanic deposits. The volcanic story extends in some form across the entire solar system. The patience of the volcanic Earth is perhaps a useful patience to take into sleep. The way the mountains are not in a hurry, the way the plates are not in a hurry, the way the slow inner heat is not in a hurry, the way everything happens at exactly the speed at which it has always happened. Let some of that patient quality be present in your own slow drift towards sleep. There is no rush to fall asleep. There is no specific moment that must be reached. Sleep arrives the way evening arrives, the way new land slowly emerges from the sea, the way the deep mantle slowly convects beneath the crust, gradually, gently, without anyone announcing it. It does not need to be summoned, it only needs to be allowed. If your eyes are still open, allow them to close now. There is nothing more to see. There is nothing more to learn. There is nothing more to remember. The volcanoes will continue to stand whether you're watching or not. The plates will continue to drift. The slow inner earth will continue its patient work. The night will continue to deepen. The slow magma is still moving in countless chambers around the world. The dormant cones are still standing in their patient quiet. The hot springs are still slowly steaming into the cool morning air. The geysers are still building toward their next releases. The plates are still slowly drifting. All of it is continuing exactly as it has on the patient time scale of the planet itself. Let the breath continue, in and out. The Earth breathes too in cycles much different from ours. The slow exhalation of volcanic gases over millions of years, the slow inhalation of carbon by weathering and burial, the slow patient breath of the planet has been doing this for 4.5 billion years. Tonight, you and the slow volcanic Earth are both alive in the same world on the same patient breathing planet. There is a kind of companionship in that. The Earth does not know you. You may never visit a volcanic mountain in person, and yet here you both are, continuing the quiet work of being alive on this single small planet, on this single small night. Let it be enough that you are here, and that the slow volcanic Earth is here, and that the patient inheritance of geology continues. Tonight, in countless places all over the soft, slow world, there is no other body in the universe that does this exactly the way yours does. There is no other planet in our solar system that does this exactly the way ours does. And yet you and the planet are both alive, both breathing, both resting. Sleep deeply now. The night will hold you. The volcanoes will continue. Tomorrow, the slow inner earth will still be at work. The plates will still be drifting. The hot springs will still be steaming. The geysers will still be building toward their next gentle releases. The slow, patient story of the volcanic earth will continue exactly as it has for billions of years. Until then, drift. Drift slowly, drift completely, drift into the slow, patient world of the volcanic earth, where the inner mantle is still circulating, where the magma chambers are still gathering, where the hot springs are still steaming, where the slow rhythms of the deep planet will carry on whether anyone is watching or not. The night is long, the slow earth is patient. The volcanoes are quiet. There is room for you to rest here in the quiet company of the patient volcanic world for as long as you need. Let your body soften. Let your breath soften. Let your mind soften, the way warm Pahohiho lava softens to flow gently across cooled stone. There is no rigid shape you need to keep tonight. The body knows how to rest. It has been doing this every night of your life. The slow volcanic earth continues. The mountains continue. Tomorrow the sun will rise over 1,000 calderas and 1,000 hot springs and 1,000 sleeping cones, and the slow patient work of the planet will be there exactly as it has been every dawn for billions of years. The world is steady. The patient ones continue. Let your sleep be one of them. Good night. Sleep deeply. Sleep slowly. The slow magma is still moving, somewhere deep beneath the crust. The dormant cones are still standing, somewhere on the patient surface. The geothermal mist is still rising, somewhere in the cool morning air, exactly as it has for countless quiet millennia. They have been here long before you, and they will be here long after. And tonight, they keep you company while you rest. Good night from the Circadian Institute.